Welcome back to the IoT course. In today's lecture, we're going to talk about infrastructures, and the first part of infrastructures is concerned with hardware and system level software of IoT nodes. So we're talking about microcontrollers, sensors, and also a bit about the basic system software like operating systems running on IoT nodes. So if we look at the infrastructure of IoT systems, we all know already that IoT systems are not just standalone devices, but they have to communicate with other devices. So with other IoT nodes, with other nodes in the internet, in the cloud, obviously, that's what the name says. So essentially, they are a distributed network system. So the IoT nodes, as shown here on the right-hand side, are nodes at the edge of such a network. That's why we also call them edge devices. And they're mostly concerned with collecting data that then has to be processed and aggregated over the network and then acted upon or stored or whatever you want to do with your data. And obviously, you need some network infrastructure to enable this. So essentially, you need maybe wireless networks to connect your IoT nodes to a router that in turn connects them to the internet. You might need some conversion of protocols, so you might have some very low bandwidth links between your IoT node and your router, and you have a very high bandwidth between the router and the internet, so it makes sense to convert protocols between the different devices. And of course, you also have the cloud infrastructure on the left-hand side, so this is concerned with coordinating the data and the operation of different IoT nodes with storing and processing data with management of the whole system. And these can obviously be devices somewhere in what we nowadays call the cloud. So just some servers, storage servers, processing servers on the internet, or even in some virtual machine farms like on Amazon EC2. So in this lecture, we're going to concentrate on the infrastructures we need for running IoT nodes, so the edge devices. And these are two parts. So one important part is obviously the hardware. So we're talking about the heart of these systems, the microcontrollers, about interfaces, and of course about sensors, which are the reason why these nodes actually exist. And we're talking about the software, so the firmware or operating system. And of course, these are network devices. So we also talk about the networking stack that's available in these devices. Of course, we cannot go into too much details here, so as always, we provide a number of links that enable you to dig quite a bit deeper into the respective topics if you're interested. So here we can see on the left-hand side a very abstract structure of an IoT node that we've seen on the previous slide already. So this is supposed to say that we have a number of sensors, like this eye should represent a camera sensor, the ear should represent a microphone, we have a thermostat and a compass for a magnetic sensor here. And all these sensors are somehow connected to a microcontroller, and this microcontroller in turn also has some sort of wireless radio usually to talk to a router and to the internet. If we take a bit of a closer look, we see we still have a microcontroller that's at the center of all of it. This might even have external memory for storing more data than this small microcontroller allows, for example, for storing measurement data over longer times or something like this. This has a transceiver, so essentially a radio connecting you to the network. It, of course, also needs to be powered somehow. That's something we completely left out on the left-hand side. So we need a sort of power source, and we're going to discuss energy in detail in the last part of this course. And the important stuff is shown on the right-hand side. So you have a couple of sensors related to the application you want this IoT node to perform. And these can either be connected directly. So these would be digital sensors. We'll see a bit more about this in a second. Or they can be analog sensors, and then we need a component called an analog digital converter to convert these analog signals into something our computer can understand. So digits, numbers, it can operate upon. So all these parts have to be present on an IoT node in order to enable the operation of that piece of hardware. So let's take a look at a specific detail here, and a very nice evaluation kit that costs around 500 kernels, but might be hard to get because of the semiconductor shortage nowadays, is a so-called development kit by a company called ST Microelectronics. So ST Microelectronics is a company that's mostly located in Italy and France, and that develops lots of different integrated circuits, including microcontrollers, which can be used on IoT devices here. And this, they have a number of different what we call evaluation boards, so boards with a lot of features that you can buy to start developing your application. And these are called discovery kits, and there's a specific one called Discovery Kit for IoT Node, and I've linked the datasheet in the references. So you see the PCB here in the picture, and you see there's quite a number of components on there. We'll go into detail what each of these components are in a bit. So the central part is also the biggest thing you see in here, the black square in the middle. This is a STM32L4 series microcontroller. So this is based on a processor core by the British company ARM. And ARM, you probably have seen already, obviously. So this is probably the microprocessor or microcontroller in many of the devices you own, including your mobile phone, of course. And this has an embedded core from ARM, which is called the Cortex M4. But this is only the CPU, the processor inside of this. A microcontroller consists of more. But we'll see details of this on the next slide. Just some key figures here. So this is not a very fast thing, but since it doesn't have a lot to do, it's okay. It runs at 80 megahertz. Compare this to your PC, which has several processor cores running at maybe 3 gigahertz. So around, like 30 times faster than that thing. And of course, it has relatively little memory. So it has non-volatile memory, flash memory, which you can reprogram, which is 1 megabyte in size. It has a bit of random access memory, so rewritable volatile main memory, so-called static RAM, SRAM, which is relatively energy efficient, but it's very small. It's 128 kilobytes only. And it can also have external memory. And here we have a 64 megabit or 8 megabyte external flash memory. So this is all, with exception of the external flash memory, contained in this big black square in the middle. And in addition, you have a number of radio technology modules, like a Bluetooth module for Bluetooth 4.1 protocol. You have a radio frequency module for different sub-gigahertz frequencies depending on the country you're in. So there's 866 or 933 megahertz. RF radio, depending on in which country you are. The radio frequencies that are allowed to use for these differ. You also have a Wi-Fi module supporting the IDO 2.11b, G, and N standards, and you can also have a NFC tag for applications that require, for example, payment or something like this. And in addition to the microcontroller and the radio, you also have a large number of sensors on this board. So you have 2 digital microphones, a capacitive digital sensor for humidity and temperature, a magnetometer which can operate in 3 axes, a 3D accelerometer and a gyroscope, also a digital output barometer, and also time of flight and a gesture detection sensor. So quite a large number of sensors on there. So if you want to build an IoT application, the probability is high that you have the required radio module on there, and also maybe 1 or 2 of the required sensors. In addition to all these components, you see there's some pin headers at the edges, so you can connect standard I/O modules to extend the functionality even further. So you have 2 rows of headers which are compatible with the Arduino AVR boards, and the header on the left lower hand side is a so-called PMOD header. This is a standard which is very common in FPGA applications usually, and there are a large number of PMOD compatible modules available on the market for very many different use cases. So just to give you a bit of a more detailed overview, where can you actually find all these components on the board? We've already seen the microcontroller is the large black thing in the middle here. And you see this is quite a big chip, and it includes quite a lot of functionality. We have an external flash RAM right to the right-hand side of the microcontroller, which can be used to store external data. So it's a flash ROM, so it can be reprogrammed. And then you have all the radios. So you already see these radios are somehow on green pieces of PCB. So these are separate PCBs soldered on top of the blue basic PCB. So usually, due to certification requirements, including an antenna and so on, all these radio modules come on separate PCBs and separate modules, which are independently certified. So you can just use them as a whole package and can solder them on top of your application IoT node PCB. So here we have the large module on the top left-hand side is a Wi-Fi module, and we also have a Bluetooth and the sub-gigahertz radio as the smaller green modules on the right-hand side. We have a large NFC antenna area on the lower left-hand side, including an NFT driver chip, and then all the very small chips you can also almost not recognize are all the digital sensor ICs that we mentioned on the previous page. And also the two silver things, the small one with the black dot on it on the right-hand side, around the sub-gigahertz radio. These are the digital microphones that you can use, well, to obviously record audio or sounds. So if we take a look at the hardware block diagram from the datasheet of that board, this is not a schematic. I think the schematics are also available, but they would just distract from the actual structure of that thing. But of course, if you want, you can take a look, because these development boards are also a very good guideline if you want to design your own piece of hardware around these components from STMicro, for example. So in the center of all of this, like on the board, also on the diagram here, is this STM32 Cortex-M4 microcontroller. And this connects to all of the sensors here on the right-hand side using a number of different interfaces. It also connects to all the radios we have here. And we have some additional features on that board, like LEDs, a real-time clock, the external memory we mentioned already. We also have debug support, so you can actually debug your application while it's running on one of these boards using a USB connected so-called SWD protocol. So SWD stands for Single Wire Debug Protocol. That's a protocol that was invented by ARM several years back in order to make it really easy and standardized to debug applications running on a physical system. So you don't need an emulator or something to debug your programs. You can just put your program on that device and debug it while it's running, including all the sensors and whatever you connect to it. You also have the expansion connectors I mentioned before, so this system is versatile and allows you to add your own hardware if you need something else or something more than what's provided on that board. So the microcontroller as a central part, just to make clear what a microcontroller is. A microcontroller is essentially an integration of a number of components. So first, it contains a microprocessor. So in the diagram here, the blue thing called the ARM core, and a number of components around it. So there's memory. So we have already seen we have flash memory, non-volatile memory, and we also have RAM on that same chip. And we have a large number of peripherals, which we can use to connect to sensors or actuators, for example. And we usually call such an integration of a processor with additional components a system on chip. And since this usually has the task of controlling something, well, that's why we call it a microcontroller. So we also just usually abbreviate it with micro C or UC just because we're lazy. So the microcontroller used here is a typical microcontroller that we can find in IoT nodes. So very many of these have a microcontroller that is using a CPU core from the ARM Cortex-M series. So there's different ARM Cortex-M microprocessor cores that you can use with different features. So it starts with the smallest one, M0, and goes up with more features and more performance. But of course, it's more expensive also. So when you go out and try to buy an ARM processor, you might be surprised because ARM doesn't actually build any processors. So you can't just go out and buy a physical ARM processor nowadays. So what ARM does, ARM is a so-called intellectual property or fabless semiconductor company. So they provide designs for tested and proven microprocessors or parts of the chip, which we call IP, intellectual property components. And if you want to build a chip based on an ARM core plus peripherals and memory, you can license this intellectual property from ARM, design your own chip and manufacture it yourself or have it manufactured somewhere. So essentially, ARM doesn't build chips nowadays, except of course for some test chips and stuff like that, but it just sells the blueprints for building chips. And so you can buy ARM-based microcontrollers from a large number of companies. So not only ST, as we've seen here, there's, for example, Texas Instruments, there's Microchip, there's Nordic Semiconductor, for example, in Trondheim in Norway. There's Infineon in Germany. So there's hundreds of different manufacturers, even small Chinese manufacturers you might never heard of before, that build systems on chip on an ARM microprocessor. The interesting thing about this is you can use the same software development toolchain like compilers, linkers, and so on to develop for all of these processors, but outside of the processor, so the rest of the system on chip. This is depending on the company who designed the whole chip, so your system on chip, and the selection of components around that chip really depends on a number of factors, like how expensive are they, do they fit on my chip, are they large or not as large, and so on. So you can actually write software for such an ARM controller, and in theory, well, you can use one compiler, but since all the surrounding components might be different, you might still need to adapt your software, for example, by using different device drivers for a different version of, for example, an SPI interface. So these ARM Cortex-Ms all have in common that they're relatively efficient. 32-bit RISC CPU cores. You can also get 64-bit cores nowadays. And the basic one is a very basic controller. So this just does essentially integer instructions, memory accesses, logic instructions. The very smallest version, the M0, can be configured to not even do multiplication in hardware. So you have to simulate it using a repeated addition. So this makes the chip quite a bit smaller and cheaper. But of course, if you have to multiply a lot, it might not be the right choice, for example, for signal processing. And then with the larger cores, you can get optional features like floating point processing in single or even double precision floating points. You can get hardware support for accelerating cryptography features. So, for example, encryption of data for, well, TLS communication over the internet. You can get secure boot and even complete secure compartments if you want to integrate or have to integrate applications from different vendors and you don't trust them with your data. You can have a separate component to run a trusted version or trusted part of your software. And you can have a vector processing unit if you have to, well, operate on vectors and matrix data quite a lot. And there's even systems on chip based on ARM processors that provide some sort of artificial intelligence accelerator for running small neural networks directly on chip on such a microcontroller. And of course, in addition to this ARM CPU core on a microcontroller, as we mentioned before, you usually have different sorts of memory, so at least flash and RAM. Some also have so-called EEPROM. So an EEPROM is a non-volatile memory that can be reprogrammed byte by byte, whereas a flash needs to be reprogrammed in larger blocks. So writing a single byte to a flash would be impractical. And of course, all these peripherals you have around the chip, which just make out the usefulness of your whole system you want to build, so your IoT node. So here's a picture from the ARM documentation, and you can see that you can actually have a upwards compatible family of processor cores here. So the smallest one is the Cortex M0 or M0 Plus. So this is the green one here, which is usually good enough for doing like general data processing, I/O control tasks, which do not require a lot of complex computations or floating point computations. The Cortex M3 can do advanced data processing, so it's a bit faster due to its internal structure, and it also has additional features for bit field manipulation. So if you do a lot of things on individual bits on words, the M3 might be quite a bit more performant here. The Cortex M4 has floating point and also digital signal processing features. So you can directly work on floating point numbers in hardware, which makes everything that requires floating points significantly faster. And DSP functionality includes things you might need to accelerate cosine or Fourier transforms, for example, a separate multiply and add instruction, which does it in one cycle, which accelerates your typical FFTs. So if you need to do a frequency domain analysis or transformation. So this is accelerated significantly. So essentially, you get quite a large number of features, which can be very useful here. So when you buy a microcontroller, you want to build a system based on a microcontroller, you usually need to define a set of features, and then you go to one of the distributor sites like Mouser or DigiKey or all the others, Alpha Distrelec. I hope I didn't forget one of the important ones here. And then you can actually mix and match. So there's a large selection of features you can have a look at, and you click all of them. And maybe to be on the safe side, because you might need additional features, you're going to over-dimension it a bit, so to use more memory than you absolutely need. And then you get a choice of different manufacturers, which all have an ARM core inside there, and then different peripherals, different features, and obviously different price points. So this market is really large. So if you start looking, there's hundreds or even thousands of different ARM-based processor or microcontrollers out there. So it's a bit hard to get started. So if you start with a development board, it's very often the case that you just continue to use something in your final product that's very similar to the board you've been using to evaluate these things, just because it makes your life easier, even if it costs a bit more. But of course, that's a question of your internal design procedures. So this microcontroller, or all microcontrollers, as I mentioned before, have a number of interfaces. So interfaces are everything that's used to help the microprocessor, so the software you run on your microprocessor, to communicate with the outside world. And there's a large number of different ones, and we'll just discuss some of these shortly. For details on these, I'd like to refer you to Peter Marvin's Embedded Systems book. We've mentioned this several times already. And of course, you can find lots of information about all of these on the internet. So a very basic method of doing input and output is called GPIO, or general purpose input output. So these are just single pins, or you can group them maybe in groups of 8, 16, or 32 pins. And these can only have two states, so logical 0 or logical 1. And usually these logical states are represented by different voltages. So a voltage around 0 volt might represent a logical 0, whereas, for example, a voltage around 3.3 volt might represent a logical 1. You can configure GPIO pins either for input or for output. So you can send a bit on a GPIO pin, so send a 0 or 1, which means you create a voltage of 0 volt or 3.3 volt that is present on that pin after you configured it. Or you can read an external voltage, 0 or 3.3 volt, and you will read them back as 0 or 1 bits respectively from a port. And you can often read or write several bits in this GPIO port simultaneously, so that makes it easier to realize something what we call parallel interfaces, where we send multiple bits at once. Very many GPIO pins can also support some very primitive form of generating analog signals, and this is done by rapidly switching the pin between 0 and 1 with a high frequency, and the frequency you switch it at, so the relation between the time it's a 1 and the summed time it's a 0, this essentially is a representation of an analog voltage level. So this is what we call pulse width modulation, and usually after pulse width modulation you need an analog component, which is a low pass filter, in order to really generate an analog voltage out of this. So this is a very cheap version, for example, to generate low resolution analog output here. So GPIOs are very versatile, but sometimes you actually want to have some more functionality on top of your pins, and this is done by different interfaces, which are a bit more complex. So one of the most common interfaces is the so-called UART, so the Universal Asynchronous Receiver Transmitter. So UARTs always transmit bits one after the other. So this is a bit serial transmission of data, and you can see the transmission of bits on the right-hand side. So a UART transmission has to synchronize the sender and receiver because both parties are only connected using a receive line and a transmit line. So essentially, you don't have any synchronizing information like a clock that tells both parties when a bit starts and when a bit ends. That's why it's called asynchronous. Nevertheless, obviously, sender and receiver have to agree upon how long in time a bit is on the line. So they agree on a common speed. So you have to configure sender and receiver to the same baud rate, what we call it. And the typical speeds are between 9,600 bits per second and maybe 115,200. There are also UARTs going into the megabits nowadays. And this synchronization is happening using the very first bit that's set to a logical 0 in a word. So if you look at the rectangle wave diagram in the middle here, you see the signal at a 1 level, and this is going down to 0. This is the start bit. And when the start bit arrives, sender and receiver synchronize, so they start counting the time at exactly that point, 0. And then over the next couple of bits, so we usually send like 7 or 8 data bits, maybe a parity bit, and then a stop bit, which is always a 1 at the end. And over that time, even if you have different clock sources, which are not exactly on the same frequency, but they might differ by like 0.5% or so, you synchronize every like 10 bits you send. So essentially, the probability is very low to run out of sync between these during these 10 bits. And then when you send the next byte, including start and stop bit, then you synchronize again. So that's why UART interfaces actually works as well as they do. But nevertheless, because of the large number of parameters, like do we have parity, how many bits do we have per word, and so on, getting serial interfaces to work and getting both sides to agree on common parameters sometimes takes quite a bit of fiddling. So very often it's very useful to have an oscilloscope nearby and just put your probe on the pin to actually look at the signal and the timing to figure out what's going wrong in your serial communication. UARTs were very common in early days with PCs even, so you used to connect your modem, maybe your printer, even your mouse, sometimes keyboards using UARTs. Nowadays, UARTs have mostly been replaced by interfaces like USB on the PC side, but they're very, very common still in typical embedded applications because they're very simple, they're ubiquitous, and every microcontroller at least has one of these UARTs on chip. There's a number of other interfaces, and well, we could spend like a whole course discussing about details of these, but at least you should have heard their names, and then you can dig a bit deeper in there. So an interface that's also very common is the so-called SPI, Serial Peripheral Interface. So this is also a bit serial transmission, but in this case it's synchronous. So you transmit a clock signal together with your data signal, and you have separate roles. So these were earlier called master and slave roles. This is not politically correct anymore. So we call them host and device node. So it's always the host that initiates a transaction and then the device responds to this. For example, SPI can be used to connect a large number of sensors. We see some sensors that use SPI, but also you can connect an SD card as storage using an SPI interface. A competitive protocol to SPI or competitive interface is the so-called I2C interface, which was invented in the 1980s by Philips. So this is for inter-IC communication. That's what the I square stands for inter-IC, the two I's. As this is also synchronous, but compared to SPI, it can be multi-controller, multi-target, so different devices on a bus can initiate communication. SPI is a one-to-one connection. I2C is a bus, so it can connect a number of devices. So these need to be addressed somehow. And there's also packet switch, so you don't only send separate bytes, but you have some more complex, but not very complex protocol on it. And it's also bit serial. It's very cheap to realize, but it's a bit strange to get started with I2C at first. There's another protocol that sounds very similar, but doesn't have that much to do with I2C, and it's called I2S. So this is inter-IC sound. So this is also a serial bus, a synchronous one, that's used mainly for connecting digital audio devices. So digital microphones, as we see in a bit, or an amplifier, a digital analog converter for creating sound, and so on. So for these, you need higher bit rates. For example, for CD sound, you have 44.1 kilohertz times 16-bit. So you already need quite a significant bit rate to transfer this. So that's why I2S is a separate interface for this. Then you can have generic interfaces. So we've already seen an ADC in our introductory slide. So an ADC, or analog to digital converter, is a component that takes an analog voltage, for example, between 0 and 3.3 volt, and then actually tries to measure that voltage and convert it into a number that's representing this voltage that's currently at the input of the ADC. So our computer can read a digit and can say we have 1.5 volt at that ADC input at the moment. And you can also do it the other way around. We've already seen pulse width modulation. So if we want a bit more precise analog voltage being generated, you have a DAC, or digital to analog converter. So this takes a digital number from your microcontroller and then actually uses a circuit to convert this to an analog voltage. Usually you could also convert it to an analog current, depending on what you need. And of course, you can have more complex interfaces, for example, network interfaces like Ethernet or RS485. You can have wireless interfaces, as we've seen. You can have interfaces, for example, to LCD displays or to screens like VGA or HDMI that you also have on your PC. You can have camera interfaces for digital cameras, and of course, USB, and so many things more. So let's talk about sensors first. And for sensors, it's good to have a definition. So this definition is from the Merriam-Webster, and Merriam-Webster defines a sensor as a device that responds to a physical stimulus, and it gives us examples: heat, light, sound, pressure, magnetism, or some particular motion. And the sensor transmits a resulting impulse as for measurement or operating and control. So we distinguish between two different sorts of sensors. So first we had analog sensors. So an analog sensor takes some physical property, like the intensity of light, the loudness of sound, the amplitude of sound, the pressure you have somewhere, like the air pressure, or the temperature, and uses a physical effect in order to transform this into an analog electric property. So for example, you could translate a temperature between 0 and 100 degrees centigrade into a voltage between 0 and 5 volts. So you would still need an analog to digital converter in your microcontroller in order to read this voltage and to get a number out of this. There's different electrical properties you can convert it to. So you could convert it into a current, so the size of current, a frequency of a sine wave signal, or the resistance of a component. So one example here is a photoresistor. And if you look at reference number 2, you'll see I finally managed to be able to cite a paper by Albert Einstein. He was the person who actually discovered the photoelectric effect. And that's actually what he got his Nobel Prize for, not for the relativity theory. And a photoresistor is a device really based on this fundamental discoveries by Einstein, that you can actually have a voltage, or in this case a current, or a resistance for the photoresistor here, that's proportional to the amount of light, so to the number of photons more or less hitting the surface of your sensor. And you can see that the data sheets for these components, like this analog sensor here for photoresistor, comes with some curves describing the behavior. So this is a nonlinear behavior here. So the resistance is very high when it's quite dark. And when you have more light shining on the sensor, you see the curve goes down. So at dark, you have some resistance that's somewhere. That's a good question if the vertical axis here is actually linear or logarithmic. I guess it's logarithmic. So you have maybe 1000 ohms. By daylight, you might have 100 ohm. And if you have direct sunlight shining on your sensor, you might have a resistance of 10 ohms. And you can measure this resistance, so you can have a defined current through it. And then you can measure the voltage the voltage difference across your resistor, and that you can put into an AD converter, and then just figure out the amount of light shining on your nice IoT node. Now, this sounds like a lot of hassle for just measuring one single property. So you need to convert maybe a resistance into a voltage and then have it run through an AD converter and then read it. So in the last decades, actually, since miniaturization and prices of electronics have gone down, people started to integrate lots of this measurement hardware you usually have in your microcontroller or as external circuits on your boards into the sensors themselves. So they built digital sensors. These still very often rely on an analog effect, but have all this complex stuff like AD conversion and creating a protocol to send out a number to your microcontroller already integrated on the chip of that sensor. So digital sensors also measure a physical property, obviously, but they use a digital interface and internal electronics to transmit numerical values corresponding to the measured entity. And again, you have some diagrams in the datasheet for digital sensors telling you which of the numerical values, like you have an 8-bit value going from 0 to 255, which physical size you're trying to measure this corresponds to. So here we have a very simple sensor, which is a so-called odometer. So this can be used for measuring distance and speeds. So we have used it in the robot you see on top here, but you can also use it, for example, if you want to have an IoT device that analyzes current weather conditions in a so-called anemometer, so a device measuring the wind speed, as we show on the lower right-hand side here. So this is very simple. So what you do is you mount a so-called encoder disk. This is a disk you see in the middle on the wheels or on a cock attached to a wheel. And this encoder disk just has segments that are alternatively colored black and white. And you shine a light on that segment disk, and either it's reflected when it hits the white segment, and then you can measure it using a photodiode, or it's not reflected when it hits the black segment. And then actually by counting the number of changes between light and dark, so reflection and non-reflection, you can actually first measure the distance, because you know each rotation of the wheel covers a certain distance. And if, like in our example here, our segment disk has 8 segments, here you know if you've seen 4 transitions from low to high and 4 transitions from high to low in your signal, then you know it's one rotation of your wheel. And then, of course, if you have this, you can convert this to a speed. So what you do is you count the number of segments since the last measurement, and of course you know the time that has passed. You obtain the distance by multiplying the wheel perimeter. So you have W wheel segments, you have a diameter of d, and then pi times d is the circumference of the circle of your, so of the outer side of your wheel. And then you know the distance that was covered, and then you can have the differential distance by just getting the number of segments multiplied by exactly that number you contained here. And if you want to figure out the speed, then you also have to measure the time. And then, of course, you divide distance by time to get the speed. And this is obviously also useful to measure angles, like, for example, in this anemometer. So you've maybe used all of these before without knowing it. So if you ever used one of these old mechanical PC mice, so with a rubber ball inside that you have to take out from time to time and clean all the stuff that you collected from your desk in there. So this is using exactly this technology. So these old, what we call mechanical mice, of course, there's also electronics inside. They use a very similar mechanism. So on the lower right-hand side, we've opened the mouse and shown you the inside. So this rubber ball actually, well, is rotating depending on how your hand moves your mouse. And this rubber ball is attached to 2 axes, the vertical and horizontal axis here, using a cylinder. So whenever your ball rotates, because you move it over your desk surface, it also rotates these cylinders. And at the end of these axes, there's one of our segment disks. And in this case, they're not reflective, but they're plastic discs with holes in there. So you have regular holes on the circumference. And then you have, well, essentially an LED on one side and a phototransistor on the other side of the disk. And whenever there's a hole, obviously the light of the LED can shine through. And whenever there's no hole, then the light doesn't show. So you can have a rectangle signal again, showing different alternating 1 and 0 sequences for horizontal and vertical axis. So you can cover the distance, you can count the distance that was covered by the mouse, and you can also get the speed. So in this mouse, you already have an integration. So this might be a little IoT device. So you have a microcontroller in there that just handles these two signals, plus some additional information like the mouse buttons and the scroll wheel. So the scroll wheel works again like the segment disks. And it handles the protocol talking to your PC like a PS2 or a USB protocol. Now, of course, if you buy a mouse nowadays, you can just notice the advance of electronics nowadays, because there's still a microcontroller in there which has quite a bit more power than the primitive microcontrollers in the old mechanical mice, because instead of this mouse ball, you now in an optical mouse have an infrared light generator and a small camera with a very low resolution of maybe 16 by 16 pixels, and this essentially just then records the light that's reflected from your desk surface to this camera. And this camera then looks at like, where have my pixels of my image, my very low resolution image, moved to? And then the microcontroller can actually figure out the movement. That's also why optical mice don't work very well on glass desks. So if you have one of these nice desks with a glass surface, you probably figured out you need a mouse mat or something. So something that's structured, so the reflection of the light actually gives different light and dark pixels in the camera picture here. So this is quite more advanced, but of course you can't really figure out what's going in. And this is a very simple method, an example of a sensor. And already the very first mice prototype built by Douglas Engelbart at Xerox PARC Labs in the late 1960s worked in exactly that way. Another simple sensor is ultrasonic sensor. So ultrasonic sensors are very common and useful in robotics. So in robotics, you want to detect obstacles. So when you have a robot moving around, you want to detect like if there's something in the way in the direction you're driving to, what's the distance to it, or maybe you want to keep a distance to a robot driving in front of you. This works like ultrasonic echolocation with bats. So essentially, the sensor sends out a high frequency signal, so it's ultrasonic, because otherwise it would disturb our hearing. And then this signal usually propagates, like we see on the top right hand side here. And as soon as it hits an object, the signal gets reflected. So the red lines are the signals sent out by the ultrasonic sender, and then the green dotted or dashed lines are the signals that you send out, which are reflected by an obstacle that might be in the way. And we know that sound has a certain speed of propagation in air. So this is also the same for ultrasonic sounds. So we can measure actually the time it takes until the signal we send out gets reflected and arrives back at the ultrasonic sensor. So that's an ultrasonic microphone that's mounted next to the sender. And then if we have the time and the speed of sound, we can obviously measure the distance. And you usually use more than one of these ultrasonic sensors facing in different directions, so you get a better, more or less view of what's happening around your robot. So that's a very simple and effective thing, and you can buy such ultrasound module from Chinese providers for as little as $1 nowadays. So what you have to do is you have to send out a signal, and then actually you have to measure the timing of the reflected signal, compare it to the signal you sent out, which of course you know well because you generated it yourself. And then the timing of this received incoming burst of signals is then related to the distance of the reflecting object. So you can figure out and then use this as an influence or as an input to your routing algorithms to enable your robot to avoid obstacles. So this might also be very useful for some sort of IoT devices, depending on what you're going to cover, what you're going to survey in your environment. Some of the sensors on that ST development board we've mentioned before. These are unfortunately a bit difficult to get information on, so we just show some details on the properties of these sensors from the data sheets. So on the top right, you see the package of this chip, And you can see it's very, very small. So this is a humidity and temperature sensor from that board, which is only 2 by 2 by 0.9 millimeters big. So very small thing. So when you try to solder it by hand, that's almost impossible, and you tend to lose it on the floor. And this has very few pins. So this has a serial interface, and it comes and supports SPI as well as I2C interfaces, so it's flexible. And this can actually measure humidity between 0 and 100%. It's based for wireless applications, so it has low power consumption. So, for example, if you have an outgoing data rate of 1 hertz, so you want one measurement per second, it only takes about 2 microamperes, which is not a lot. You can select the output data rate, so you can go up to 12.5 hertz if you need more or higher timing resolution. The accuracy is relatively good, around 3.5% relative humidity in a certain range. And you also have a temperature sensor, which is in usual room temperature, so between 50 to 40 degrees centigrade. And the accuracy is about half a degree. So this uses an embedded analog to digital converter because all these measurements are taken analog and using analog components. And this embedded analog to digital converter then essentially provides the digital information, which is then sent out as 16-bit value via either SPI or I2C, depending on how you configure your chip. And then if you connect this to the SPI or I2C pins of your controller and write a bit of device driver code, then you can automatically get an update of your humidity and temperature values, for example, every second. Another more complex example is a magnetometer. So this actually is able to measure the Earth's magnetic field, and this can be used to determine the orientation of a device. So for example, if you have a floor plan of a factory floor and you want a robot to be able to navigate there, if you have the direction to north annotated in your floor plan and to provide this to your robot, then your robot can actually figure out in which direction is it driving. Is it driving north, south, east, west, or anywhere in between? So these sensors are very flexible. They're also very small, so they're also only 2 millimeters on the outside, and they have a bit more pins here. So you can get single conversion mode, so you can actually trigger this device to do one measurement only when you need it. This is, of course, less energy consuming than when you have continuous mode, where the magnetometer just gives you your orientation with a certain frequency. You also have a 16-bit data output here. This can also generate interrupts automatically. Like the previous sensor, this can be configured to use SPI or I2C. And what's interesting here is that this is using a micromechanical or MEMS component. So essentially what you do is you integrate mechanical components on your chip by using acid to remove certain parts of it, and then you can measure things like vibration or the movement of a certain particle as a reaction to a change in magnetic fields, because you're just turning your robot around the axis, so your magnetic fields change. So some components move to other places inside of your silicon chip. And these things then, these effects then generate electrical signals, analog electrical signals, that you can then convert to a digital signal and then send to your microcontroller again. So these MEMS sensors are very common nowadays. They can be built very small due to using features of semiconductor manufacturing instead of classical mechanical devices. And they can also then be built relatively inexpensively. Digital microphones are yet another MEMS device. So you probably know that sound is transmitted through the air as a sequence of pressure differences. And the thing is, you need to convert these pressure differences to a digital signal indicating frequency, at least the frequency of the sound, and maybe also the amplitude. So on the lower right-hand side, you see that there's a membrane in this device. This membrane just reacts like, the membrane in your ear to the differences in air pressure here. And you can measure these and convert these to digital signals again. So the interesting thing is that the protocol here is quite a bit different. So you can send it using this chip here as an I2S signal. So I2S is a specific inter-IC sound protocol, but you can also use a very simple form called pulse density modulation, PDM. And this is a very nice form shown on the lower part of the slide here. So essentially, the higher the amplitude is, the more 1 bits you send in a certain amount of time. So you can see this red sine wave here, and wherever the sine wave has its least amplitude, so like the two parts with the white bits, which should indicate a 0 bit, you just send zeros, indicating it's a very low amplitude, and then your actually amplitude goes up. So what you get are more and more 1 bits dispersed over this time. And when you hit the maximum amplitude, you just get a continuous sequence of 1 bits. And then by, well, reading those time after time, because you know the sampling frequency of these bits, then you can also figure out the frequency and, of course, the amplitude of that signal. And the higher your sampling frequency, obviously, the more precise your information about amplitude and frequency will be using pulse density modulation. Another component we've seen on the overview slide at the beginning is power supply. So, of course, all these electronic circuits and sensors need power, and power supplies for IoT nodes consist of a number of components. One important thing is a voltage regulator. So you have different components from different manufacturers, maybe produced using different technologies. So these might require different supply voltages. So you might have some 3.3 volt components, some 5 volt components on your PCB that makes that the basis of your IoT node. So this means you need to regulate your voltage because a device that's supposed to run on 3.3 volt won't be very happy with running on 5 volt, and you could destroy it using this. So the problem with early voltage regulators is that they were essentially just a large voltage divider using resistors. Not quite, but almost. So essentially all the voltage you didn't need, given the current you were required, was converted into heat. That's a waste. So nowadays you have more advanced voltage regulators, so-called low drop regulators. These are DC linear voltage regulators, and you can regulate the output voltage even when the supply voltage is very close to the output voltage you require, and they use advanced circuit techniques to minimize the power loss, and with this also to minimize the heat dissipation. So essentially these things are required, and using these low drop regulators you can save quite a bit of power and in turn energy. Now, of course, all this energy and power has to come somewhere. So, well, if you don't have a battery or, of course, some sort of cable providing power or energy, then you can use energy harvesting. So when you don't have a permanent energy source available, you can retrieve energy from the environment using some physical effects again, like wind energy, solar energy, thermoelectric energy, and so on. You need to store energy somewhere, especially in mobile devices, but also in energy harvesting devices. So we have batteries, which can be rechargeable or non-rechargeable and maybe need a charge controller. And for energy harvesting devices, there's instead of a battery, a very interesting technology called a supercapacitor, which can serve as a short-time storage for small amounts of energy. Then that helps you keeping your system running for a bit longer, even if the sun is no longer shining on your solar cells. We'll discuss more on power and energy and also analyzing power and optimizing power and energy consumption in the last part, part 5 of the course. Finally, we have radios. So we've seen that most IoT edge devices are nowadays connected using wireless radio technology, and there are many different technologies. So we can differentiate between 3 classes. The first one is technology adopted from PC systems. So we have Wi-Fi, which is officially called IEEE 802.11. So a family of standards for Wi-Fi, wireless networking technology. This usually runs in some of the so-called ISM bands, so the freely available bands. You don't need a license for industrial, science, and medicine applications. And there's usually 2 frequency bands. One is around 2.4 gigahertz, the other is around 5 gigahertz, and you can get transmission rates between 2 megabits per second and like 300 or even more nowadays, depending on the technology. So this is quite fast, but also quite energy consuming. You also have Bluetooth and Bluetooth Low Energy, which can run in an infrastructure mode, so with a central device controlling Bluetooth communication, or in a mesh mode where each of these Bluetooth devices can talk to each other. This is usually running at 2.4 gigahertz. Then, of course, you can have cellular, mobile phone networks, so all the technologies we have nowadays, 2, 3, 4, or 5G. These are relatively expensive. You need a subscription to run them, so you need a SIM card in your device. So you actually create costs when you use this. But for some applications, when there's no other infrastructure around, you may need to use this. So I've seen this used in Trondheim. So there's a bike rental service in Trondheim, and they have equipped all their bikes with a 3G mobile sensor or mobile radio. And what the mobile phone providers in Trondheim didn't tell them is that at the end of 2020, they were phasing out 3G mobile connections in Trondheim. So the radios had an automatic fallback on 2G, which was still available. But of course, this was far too slow for all the amount of data that was transferred from the bikes. And of course, the bikes had to use a mobile phone infrastructure because they were moving around the city, and the owner of the bikes wanted to know where these bikes ended up, if they were returned on time, and who is actually currently riding that bike. So if you operate devices over a long time, you have a dependency here, which might be quite difficult. And finally, you have special networks built for IoT applications, which are usually low power networks. So you can have wide area networks like called LPWAN, so low power wide area networks, for example, LoRaWAN. Or you can also have short range and mesh networks like Zigbee, Z-Wave, and Thread. So a lot of technologies here. We'll discuss more about these technologies in the upcoming next lecture here. What's interesting and what you've seen before is that these radios are usually bought and implemented as separate subsystems on their own little PCB. So they have their own controller handling all the radio reception and transmission, error correction, and so on. And these usually then communicate with the central microcontroller using a UART, I2C, SPI, or in your mobile phone, they might even use USB as an internal communication medium for high-speed data transfers. So more on this, as I said, in the next lecture. So we've talked about hardware all the time. One important other part to get your system running, of course, in addition to your application for your IoT node, is system software. So your IoT node will have to work on separate tasks at the same time. So it will have to acquire data from one or more sensors. It will have to process this data, for example, doing a Fourier transform to convert whatever a signal into a frequency spectrum. It needs to provide drivers to communicate with sensors and radios. Your IoT node needs to handle the network protocols to talk to your router and machines on the internet. It has to receive data, so requests from the network. And of course, it has to send replies as data to the network. So your system software, of course, you can build IoT nodes without any system software by hand, which is what we call bare metal programming. But using some sort of system software makes life quite a bit easier because it helps you doing tasks. So this system software running on your IoT node is responsible for scheduling the different tasks in the system, so finding an order which is useful, and also, for example, might adhere to real-time constraints in your system. It needs to be able to react to incoming data from sensors and the network. It should provide some abstract interfaces to sensors and other I/O to your application, so you don't have to communicate with the device directly, but maybe have an interface that just tells me, give me the temperature or the pressure or something. And optionally, if you have, for example, software that you obtained from different vendors and you don't really trust that software because you couldn't read all the source code or you didn't understand what was going on, or maybe you just got a binary, then you might also want to protect activities against each other. So this is obviously closely related to security, which we'll talk about more in part 4 of our lecture. So modern microcontrollers actually have quite a number of features for protection, encryption, and isolation of different pieces of the software against each other, even on such a small processor core like the ARM Cortex-Ms. So that's the Cortex-M33 and Cortex-M50 series. You see more digits behind the Cortex-M means advanced features. So, which operating system should you choose for your IoT device? This is a difficult question. So there are several hundreds of embedded operating systems you can find out there. lots of commercial ones, lots of open source ones. Many of these actually have additional features, so real-time guarantees a real-time capital scheduler. So if you have something that's timing critical on your device, like a robot, for example, you can guarantee that if you have a sensor input, that your reaction will come after a defined worst case time, so you know your robot is fast enough to react to whatever's happening on the outside. And one example OS that's nice because it was developed here in Sweden 20 years ago by a student at the Swedish Institute of Computer Science, Adam Dunkels. And this is called Contiki. And this is an operating system for network memory constrained systems with a focus on low power wireless IoT devices. Well, that's exactly what we're talking about, obviously. Development has been started 20 years ago in the context of Adam's PhD thesis in Stockholm. And essentially, this was open sourced and is, yeah, people continue to develop this. And it's a very interesting thing. And it's used for a large number of use cases. So it's used for commercial street lighting, for sound monitoring, for smart cities, for radiation monitoring, for alarms, just as some examples. And you can get it as open source software. It's released under the BSD 3-clause license. So this means in comparison to the GPL license, for example, the Linux kernel is released under, that you can just use it, you can modify it however you want, and you don't have to open source your results. Of course, it's still nice if you do it, but the BSD source code license doesn't require you to do this. I'm not going into details on this. If you're interested, let me know. I can give you some links and hints on open source licensing and the caveats, especially if you're from industry and would be interested in using some of these licenses in your software licensed under some of these licenses in your product or software. Contiki has been ported to a large number of different hardware platforms, from very small 8-bit controllers to 32-bit controllers, and it's still small and easy to use, which makes it a nice platform. And of course, there's a lot of support and open source applications, tools, and examples out there. So Contiki is a bit special. So compared to very many other operating systems, Contiki actually can dynamically load and replace code, so applications at runtime. So if you have a device, for example, running in 2 different modes, you can switch between the modes by loading either one application, and when that one application is done, you can switch over to the other application. The kernel is event-driven, so it just reacts to external events, like things coming from a sensor or the network, and it allows the system to sleep most of the time. So sleeping just means in this context that we're running in a very low power mode here. It doesn't have to do preemptive multitasking, it can do cooperative multitasking, but if you want preemptive multitasking, Contiki is flexible enough so you can optionally link preemptive multitasking as a library, as a component, which is one of the very special features here. So as static components, you always have the Contiki kernel, so the base of the system itself, a program loader, which is responsible for loading and unloading all the dynamic components, a runtime core for your language, so responsible for starting programs written in a certain language, and you usually have a communication stack for device drivers, and then you can dynamically load and unload components like services for your network, like a web server, for example, as a loadable library, and application processes. So here on the right-hand side, you see a typical structure. So on the bottom, you have the hardware consisting, as we've seen, of a CPU, radios, sensors, a frequency source, which you can manipulate, for example, to slow down your CPU to save energy where there's not a lot to do, and maybe other things. You have a driver for each of these hardware components that's responsible for controlling this hardware, and you can access these from the Contiki core, so using a loader, using what's called proto-threads, so a cooperative multitasking scheme, and also a network stack. And then on top, you can have applications, that's the stuff you provide yourself, as a value add to the whole system. And you can have node management, so you can essentially have a number of features like updating the software. You can configure your sensors for different features, configure your network, and manage your network data as part of Contiki. So it looks like this is a nice integrated solution for your IoT nodes. So Contiki is ported to very many controllers, and is not different to port it to a new one in case you need it. So it should be able to run on very small, so very inexpensive microcontrollers, even 8-bit devices such as the AVRs, from Arduinos. And especially for IoT devices, we talked about non-functional parameters before, and we've seen power, energy consumption, execution speed, and so on. But what's also important, especially for these very small devices, is that you also have a small code size. Because if you have a large code size, first, it takes longer to execute, but second, it just might exceed the amount of memory you have available in your system. So most of the code is in non-volatile memory in flash, but you also want to reduce the consumption of RAM, for example, by storing variables as smaller data types. So storing an 8-bit value in an 8-bit variable instead of a 32-bit variable to save 3/4 of the memory for that variable here. And if you look at the lower left-hand side here, you see the code size of Contiki is very small. So on an AVR 8-bit controller, you have around 1 kilobyte of code for the kernel, 128 bytes for the service layer, 600 something bytes for multi-threading, 90 for a timer library, and there's some other stuff like replicators. So you're below 4 kilobytes for your operating system. So with the a bit larger AVRs, which have like 16 kilobytes of flash, you have quite a lot of memory left over for your application. For the MSP430, that's a Texas Instruments 16-bit microcontroller. You see the 16-bit controller makes your code a bit smaller because it can handle larger data a bit differently, but in the end it comes out almost the same, plus minus 2 bytes. And the RAM usage is dependent on a number of parameters here, but you see this is in bytes. So this is very small, so it has a base usage of about 230 bytes. And then, depending on the number of the events you can have, so the size of the queue for your events and the size of the stack for your threads, this adds to the number of bytes, but we're still like in several hundred bytes range. And the interesting thing is that Contiki allows you to partition your application then into core. So this contains the kernel, the program loader, the runtime, and the communication service, as we've mentioned before. And then it can have different loaded programs, which are all available in Flash because you're usually not downloading code over the internet while your sensor node is running. So it's all in Flash whenever you deploy your node. But the RAM that's used by these loaded programs, that can be swapped in and out just as needed when you swap in and out the program, because the RAM is usually quite significantly smaller than your Flash. So RAM might be a scarce resource. So this loading or unloading of module enables you to have a more efficient management of RAM memory, though it's of course nowhere close to what you do on modern high-end desktop or server processors with virtual memory and so on. But still, that's a very nice system, and that's something you don't get with many of the other like small embedded real-time operating systems. So in addition to the system software, we need a network stack in order to talk to the internet. We're talking about the Internet of Things after all. So like with the operating system kernel itself, we need a small and efficient network stack that should still have enough features to enable us to talk to the rest of the internet, so to talk to our router. We could implement features like having a special protocol talking to a router that understands that protocol and then translates this to standard internet protocols, but that would be quite a bit of overhead. The attractive thing about IoT is that the IoT nodes somehow can directly talk to the internet without translating protocols. So this was also developed by Adam Dunkels. There's two versions, one called LWIP, lightweight IP, and the other called UIP, so micro IP. So UIP is the smaller version, which is actually useful on small 8 and 16-bit microcontrollers with very little memory. So it's a complete TCP/IP stack and now supports IPv4 and v6, and it's implemented as a library that you can use on top of Contiki. It requires very small amounts of code and RAM, but in order to achieve this, it has a very unusual programming model you also see shown on the right-hand side. So as Contiki itself, UIP is event-based. So it's not your application controlling the network stack, but it works the other way around. So whenever something is happening on the network, so an event comes in, then actually your application is implemented as a number of C callback functions, and these are called by the UIP stack in response to certain events that happen. So it's turning all of this on its head, and this helps to save energy because if there's no network traffic, maybe you don't have to do anything. And it also helps to keep the operating system and the IP stack in control, because if you don't have preemptive multitasking, for example, then an application that would like wait for something would not be able to receive network packets. So if we are waiting for data from sensors, we would be unable to receive network packets without any elaborate like interrupt handling and stuff like this. So this event-based approach actually helps us to build a simple software structure that can still work and provide TCP/IP on very small microcontrollers. You can compare this to what you might be used to if you've done network programming before. So the very standard interface used on Unix, but also on Windows commonly is the so-called socket interface, which was invented in Berkeley with BSD Unix. And this is not really suitable for small systems because this requires you to do multi-threaded programming. This requires you to have preemptive multitasking, complex device drivers, and it simply wouldn't fit into memory because of all the overhead with socket and buffer handling. A bit more complex TCP/IP stack with more features is LWIP. So as UIP, it also supports IPv4 and v6, but you can also have more protocols supported here. So LWIP comes with a bit of a larger code size. You need around 40 kilobytes, depending on the target CPU, but this already includes IPv4, TCP, UDP, and also additional protocols not available in UIP like ICMP, which is, for example, used to implement ping, some APIs and support functions. Both UIP and LWIP are, like Contiki, licensed under the BSD license, so you can freely use them without publishing your source code if you like. But of course, nobody hinders you from publishing the source code of your modifications. So LWIP has a more conventional programming model that is similar to sockets, though still a bit simplified compared to full BSD sockets. But this in turn requires multi-threading in the operating system and application, so it makes things a bit more complicated. LWIP can not only be used with Contiki, but it's used as a TCP/IP stack in quite a number of systems. So we have commercial products from Intel, from Analog Devices, Xilinx TI, STMicro, and Freescale, all using LWIP. But we also see it used in some open source operating systems. So there's Reactors, which is attempting to build an open source Windows NT clone, and a microkernel-based operating system called Gnode from a company in Dresden in Germany, based on the L4 microkernel. And here we've shown not kilobytes like in the previous slide, but lines of code. And we see that TCP actually makes up almost half of the complexity of it. So TCP is the most complex protocol in here. So if you, for example, build sensors that would be able to communicate using UDP only, that's absolutely possible. You would just save quite a bit of code, like you would maybe save like 15 of the 40 kilobytes. And then you see all the other functionality is actually implemented in an amazingly low number of codes. So the IP protocol is less than 200 lines of code. UDP is even less. ICMP is 90 lines of code. So if you're interested in implementation details, you can not only read the linked papers and Adam's PhD thesis, which are freely available on the internet, but there's also a book by Richard Stevens, TCP/IP Illustrated. It's a 2 or actually 3-volume book nowadays, which are 1,000 pages each for the first 2 volumes, which describe all the TCP/IP protocols and the implementation in BSD Unix in detail. So if you want to dig deeper into network protocol analysis and optimization, that's what I can recommend. These books are really, really valuable. But of course, for just using it, you don't have to dig as deep, but you can just use the provided abstractions in UIP or LWIP. Of course, there are also commercial TCP/IP stacks out there, but I would say UIP and LWIP are usually better tested and more widespread than any of the commercial solutions you can buy out there from different vendors. So let's conclude. We've seen IoT nodes that look simple and small are, in practice, very complex devices. So the configuration of the device in your final product will depend on your use case. So you have to select the controller, external memory, the sensors, the radios you use. And we've seen there are development boards that you can use that have a lot of different features, like different radios and different sensors. So you can experiment. Of course, in your final product, for cost reasons, you want the minimal required hardware present, so just a subset of everything. We've seen there are different sizes and feature sets of microcontrollers and a large number of different sensors. We've seen an overview of system software of the operating system, what it has to do, like scheduling and memory management, providing device drivers for sensors for the network. So you as an application programmer for your IoT device have an easier time getting the application to run. And of course, it has to provide a network stack or interface to a network stack. And we've seen two different versions of a TCP/IP stack with UIP and LWIP. And which one you use depends on your requirements and obviously also on the hardware capabilities of your device. One interesting requirement we'll talk about more in part 4 is something Contiki provides, the over-the-air update. Like nowadays, even in your car or something, all the embedded devices have lots of software running on it, and they may have bugs and also security problems. So you actually want to update them, what we call in the field. So when they're deployed at a customer site. And essentially, for IoT devices, obviously, since they're connected to the internet after all, you can provide an update functionality. But of course, this update functionality has to be secure and safe. So an update should not kill your device by updating software that doesn't work and then doesn't enable another update. That's what we call bricking. So you can just use your device as a brick afterwards. And of course, it has to be secure. So nobody else tries to actually upload software to your IoT nodes, because this might be able to create large scale botnets, for example, for running distributed denial of service attacks or something like that. That's obviously something you don't want. So we'll talk a bit more about over-the-air firmware updates for bugs and security fixes in part 4 of the course. So this concludes today's lectures. Thanks for listening. Here are the references. So today it's a mix of data sheets, of papers, and of course, especially for all the Contiki and LWIP, UIP software. You can also find links to GitHub. So we've not listed them there, but they can easily be found by searching on the net. So thanks for listening today. I hope you found it interesting. And the next lecture will then continue with network hardware and network protocols. So everything that has to do with wireless. Until next time, bye.